In this video, we're going to start talking about number theory. So this is going to be the start of chapter 4, where we start a little bit about number theory. This will give us a good opportunity for us to employ some of the proof methods that we just learned about in chapter 3 in the logic and proof section, or the logic and proof chapter, I should say. And so we're going to start with some definitions. And really, I want to hammer in on the definitions and proving things from the definitions in this chapter. That's going to be a really big idea for us. So what we're going to do is really throughout the entire chapter, I can't think of any exception to this, but if there's an exception, I'll say it. Every term, every value, every variable is an integer. Okay, so every variable is going to be an integer here. So whenever I talk about x, y, z, m, n, a, b, whatever, everything is going to be an integer unless I say otherwise. Yeah, so we're going to say that an integer a divides an integer b if there exists an integer k. So if there exists an integer k such that b is equal to ak. So that's what it means for a to divide b. So for example, 3 divides 12 because 12 is equal to 3 times some integer. 7 divides 7 because 7 is equal to 7 times some integer. Everything divides 0. So 10 divides 0 because 0 is equal to 10 times some integer. One little quirk and one disagreement that I have with a few authors is that I say 0 divides 0 because this also has the same pattern. So 0, for example, is equal to 2 times 0. Nothing divides 0 except 0. So of course you can't have 2 divide 0. So 2 does not divide 0 because it doesn't matter what integer you multiply. Did that backwards. It doesn't matter what integer you multiply. It doesn't matter what integer k you have. You're never going to have a solution to this equation. So that's why 2 does not divide 0. But these are all good examples. This is our notation that we're going to use. So for example, 5 does not divide 12. Again, because there is no integer such that 5k is equal to, there's no integer k such that 5k is equal to 12. So 5 does not divide 12. If you avoid this 0 dividing 0 business, one thing that you can say, so if a is positive, then, well, I can actually be a little bit stronger. As long as we don't involve 0, then a divides b if and only if, so if and only if b over a is an integer. Okay, so a divides b if and only if b over a is an integer, as long as a is not equal to 0. So again, excluding this silly situation where 0 divides 0 just because it fits the pattern. This is why a lot of people exclude that rule. Anyways, that's what it means for a to divide b. As a few examples, we're going to say that an integer x, or whatever variable you want, but an integer x is even if 2 divides x. This is really what it means to be even, is that 2 divides x, right? There exists an integer k such that x is equal to 2k, right? And so an integer is odd. So likewise, an integer is odd if 2 does not divide that integer x. Okay, so this division sign, or the division sign with a line through it, is how we're going to denote the divides or does not divide. Okay. One other proposition that I want to talk about, and this is something that I'll leave to you as an exercise, but one other proposition is the following. This is written up really nicely in the notes, so I'm just going to give a sketch of what's going to happen here. But every integer divides itself, so that's true for all integers x. I'm using our for all notation. Remember that we talked about this in the quantifier video. 1 divides every integer. So that's again for all x. Every integer divides 0. So again, for all integers x. And If 0 divides some integer, that implies that x has to be 0. So in other words, if x is non-zero, then 0 does not divide x. I will leave it to you to prove all of these and think about how you could prove these. These are all really direct proofs, so there's a big hint there. Okay, so proof, I will leave that to you to fill in.